Now let's talk about partitioning. We want to select the last element of a list as the pivot and then rearrange the other elements around it. So the end result should look like this. In the left partition, we're going to have the items that are smaller than the pivot, and in the right partition, we're going to have the items that are larger. So back to the original array, let's see how we can solve this problem. We need two pointers or two variables here. We use the first pointer to iterate over this array. So that's going to be our typical loop variable. We can call it I as usual. We use the second pointer to mark the boundary of the left and right partitions. So we call it B as in short for boundary. You can think of boundary as the end of the left partition. Initially, we set it to -1, which means the left partition is empty. So the right partition starts from index 0. As we iterate over this array, if we find smaller items, we move them to the left partition and bring the boundary forward. Let me show you. So I is 0 and boundary is -1. Now we're going to iterate over this array, reading one item at a time. If the current item is smaller than the pivot, we should move it to the left partition. We're going to do that using a swap. Otherwise, if the current number is larger than the pivot, we ignore it and read another number. So the first item is 15. Is it smaller than the pivot? No, it's not. So we keep going. We read 6. Is 6 smaller than the pivot? Yes, it is. So we should move it to the left or the small items partition. First, we need to increase the boundary because currently it's set to -1, and it's like there is nothing in the left partition. Again, you can think of the boundary as the end of the left partition, okay? So we bring the boundary forward. Now in the left partition, we have a number that is larger than the pivot. We need to swap this number with the smaller number that we just read. So we swap 15 with 6, and now 6 is in the left partition. Again, we repeat. We read the next number, 3. Is this smaller than the pivot? Yes, it is. So again, we increase the boundary. Now the last item in the left partition is a number that is larger than the pivot. We need to swap this number with the smaller number that we just read. So we swap 15 with 3. Our left partition is getting bigger. One more time. We read 1. This is also smaller than the pivot. So we increase the boundary and then do a swap. Now we read 22. Is this smaller than the pivot? No, it's not. So we should leave it where it is, which is our right partition. We read 10. This is a smaller number, so we should increase the boundary and swap 15 with 10. We have read all the smaller numbers and put them in the left partition. Now we should put the pivot after the left partition. So once again, we increase the boundary and swap 13 with 22. Now 13 is in the correct position and boundary holds its index. So this is how partitioning works. Now let's do complexity analysis. We need to look at the cost of partitioning an array and how many times we can recursively partition the resulting left and right partitions. What is the time complexity of partitioning an array with n items? It's O of n because we have to iterate over all the items and swap them if necessary. Now, how many times can we partition an array? Well, that depends. Let's imagine that once we partition an array, the pivot ends up in the middle and we get two nearly equal sized partitions. So we have divided this array into half. How many times can we divide an array into half? Log n times. Now, what if the pivot doesn't end up in the middle? What if the left partition is really big and the right partition is so small or non-existent? Here's an example. In this array, if we pick 7 as the pivot, it will stay where it is. So we'll only have a left partition that has one less item. Next time we partition this array, again, 6 will stay where it is, so we'll get a left partition with one less item. How many times can we partition this array? N times. This is our worst case scenario. So if our array is sorted in ascending order and we pick the last item as the pivot, the number of times we can partition this array equals n. The same situation happens if the array is sorted in descending order and we pick the first item as the pivot. Now to work around this, we have a few solutions. We can pick the pivot randomly, or we can use the middle index, or we can use the average of the first, middle, and last items. These solutions don't prevent the worst case scenario, but they reduce its likelihood. So the number of times we can partition an array can be log n in the best case scenario and n in the worst case scenario. And with that, the time complexity of quicksort can range from O of n log n to O of n squared. Overall, with a good pivot selection, we can say that quicksort runs in O of n log n on average, and it's a fairly efficient algorithm. Now, what about the space complexity? Well, Unlike merge sort, with quicksort, we are not allocating new subarrays. All the partitioning and swapping of items is done in place in the input array. However, we need to count for the space required for recursive calls, because each recursive call requires some space on the stack. The Java runtime uses the stack to keep track of these recursive calls and go back to the previous call. Now, how many recursive calls are we going to have? It's like asking how many times can we partition an array. You already calculated it. So the space complexity of quicksort is log n for the best case scenario and n for the worst case scenario. Overall, we prefer quicksort to merge sort because they both have O of n log n time complexity, but quicksort requires less space. All right, enough theory. Now it's time to implement quicksort. So spend 20 to 30 minutes on this and then come back see my solution.